So let me ask some question to Alexei. As far as I understand, you propose some Lagrangian high-spin fields. Can this Lagrangian reproduce a cubic vertex, standard cubic vertex?
Okay, it reproduces standard cubic vertex multiplied by integrating by this integrating multiplier omega. See, we get some part of high spin gravity equations of motion. So
Okay.
in this sense, it reproduces. But
okay, thanks.
May I make a comment on this?
Yes.
Well, actually, the way that one can, in principle, introduce Lagrange multipliers this way, it was proposed in a very old paper of mine, where actually the first deformation to equations were considered. And for some reason, I still believe that this is not the proper action for the higher spin theory. So that's why I phrased this very directly in that paper, I think. And I think this is the same idea, just to introduce this kind of Lagrange multiplier. Okay, so if Yasha is not ready, so that was the comment. If you, want to say something, that's fine. Why don't you say?
Anyway, it is interesting to see what happens if we try to find such
integration. No, I don't mind. I just say
to what extent we can reproduce.
It's a very new idea to do.
It is not new, but the classification is new. Nobody find all possible admissible Lagrange multipliers for high spin gravity equations of motion.
Well,
maybe it is not new, but it is a classification. It is not just.
No, I'm saying what I'm saying. I said the particular point, and this is the point. So this point that one can consider Lagrangians of that form is not new. So another question I'm wondering, you referred to Wigner for deformed oscillator. I'm also referring to Wigner for deformed oscillator, but I was never able to find this algebra in his papers. Do you know exactly the reference where this algebra appears in Wigner's paper?
The number of formula, I don't remember the exact number, but
I appreciate if you would just send me a message with the exact reference, because maybe I was missing something.
Okay, I will send you.
I really admire. I appreciate that he made a great.
No problem. I will send you. Yeah, of course.
Yeah. Okay. Also, I want to make the following comment is that Alexei mentioned that it is very surprising that there are some exactly conserved charges at the nonlinear level in higher spin theory. Indeed, when I found that these charges can be constructed, I was surprised myself. But then there is a good explanation why does this happen, and why this does not happen in other theories. Well, the point is that these charges, as they are defined, they are non-local. And to go from the boundary charges, which are local, to inside of the bulk, this extension inside is non-local. And that's why they are never seen in local field theories. And it is hard actually to construct them. So that is, I think, the real explanation. And this non-locality is, just a feature. I'm not saying it's bad. I'm not saying it's good. This is how it is organized. And actually, it's very interesting. And also what is interesting is that in the near to the boundary of space-time, at infinity, let's say, they become actually local charges, and these are asymptotic charges in black holes.
So please, some questions, comments to all today's speakers.
Joseph, may I make some organizational comment, actually?
Yes.
I would like, since the schedule for these talks was corrupted and some participants could miss the beginning of some part of the talks, I would like to say that in a few days there will be a YouTube translation for all talks where everyone can check all missed talks and things like this. So you will get information about this. Thank you.
Okay, let me ask some question to Yasha Neyman.
Yes.
If to follow to analogy with electrodynamics, to construct interaction, you can write current on one volt line, current on the second volt line, and the green function between them. So to do this way, we need, because you take into account all spins together, you need a green function for the Vasilyev's equation. Is it true?
So let's see. So first of all, we are happy enough with just the Fronsdal equations because this is at linearized level, and then the statement is at least effectively yes. So I didn't do it literally in that way. So I just write down the solution for the field as induced by the entire world line. But it is probably true that this can be expressed as an integral over the fields induced by every separate point of the world line. And I would imagine that there should be a Green's function that makes sense, at least at leading order. But somewhere you will still need for consistency the conservation of the current, of course, which is expressed in the world line being geodesic.
But you consider some kind of constant field approximation, because in general you have to take some time dependence, x dependence for the interaction.
No, the field is certainly not constant. It is constant along the direction of the world line that is producing it. But let's say the scalar field is just 1 over r, where r is the distance from the world line. And similarly, the spin 1 is just the electrostatic field of point charge. So there is a space-time dependence, of course. And it becomes tricky once you have 2 of the world lines. So the field of 1 is radially symmetric with respect to its direction, but the other can point in a different direction. So there is some work to do to integrate the interaction action. But so behind the scenes in flat space-time, this work is doable explicitly. Well, in ADS, I'm not smart enough to do the integrals directly, but I can guess the answer either from higher spin symmetry or from the boundary correlators, and then check numerically that it agrees with the integrals.
Okay, thank you. So, more questions, comments?
Well, I had a question to Yasha before.
Yes, please.
So yeah, I was wondering like about this property that linear solutions get promoted. So in gravity, this is true that solutions to 3 equations, they are promoted to full nonlinear equations, right?
Yes.
So I wonder whether it's true for Vasilyev equations, first thing, and another thing, whether like this conclusion was kind of affected by some like new developments, recent developments, you know, like shifting these operators that allow you to construct interactions.
Okay.
Or it's for you, it doesn't really matter.
So first, the easy part is that yes, you do get nonlinear solution to the Vasilyev equations. I guess this is a question more to Misha than to me. But it does work. I'm not using it, but it's kind of important that it exists. Now, recent developments I see two kinds of recent developments. The first is just a shaking of our confidence that we understand what a nonlinear solution of the Vasilyev equation even means. Okay, on the other side, there are the efforts by Misha and friends to improve the situation by basically completing the definition of the theory and working out how to handle the integrals in Z space. So none of this, as far as I understand, affects the fact that the nonlinear solution is a solution, merely the question of how to interpret it. As far as I'm concerned, I'm not smart enough for all this. So my job is to look for some cheats and for some easy ways to extract physical results and also physical interpretation. Say what the object of the singularity is and figure out how two of these can interact, for example, without going into the nonlinear Vasilyev equations, just by some combination of Fronsdal theory coupled to point particles, global higher spin symmetry, and holography.
But still, is it true that charges, higher spin charges, in this case, are not independent due to non-linearities? So if the theory was linear, you would just take a superposition of like black holes in each sector with fixed spin, and charges could have been independent. And for you, relatives, like values of charges, is something that matters.
Right. So what you can do certainly is to write linearized fields of a point charge with any values of the charges of different spins that you like. Okay. Now there is something special about this particular pattern of charges, and there are many ways of saying what this something special is. Okay, so the original way of saying it is that for this particular pattern, the kind of linearized master field is simple enough that we can upgrade it into a nonlinear solution. Okay, so from our work, you see a couple of other ways in which it is special. So it is special in the cancellations of UV divergences and interaction when two of these guys come close together. That uniquely fixes the pattern of charges. And it is special it's special in that only this particular pattern of charges describes a bilocal boundary operator. And in another way, which is kind of subtle and they didn't get to in the talk at all, is that this construction, the Penrose transform that makes linearized solutions, it is supposed the original Penrose transform makes honest linearized solutions without sources. So it is quite unusual that it produces this solution that seems to have a source. And this procedure does not work for the individual spins. It only manages to work for some subtle reasons when the entire combination is taken together and in this particular way. So again, this central singularity with these particular charges is on one hand, it is a source term. It's not just part of the free higher spin multiplet. But on the other hand, it's somehow maximally close to not being a separate thing, being just an organic part of the higher spin multiplet. It's masquerading as just a free solution that can be obtained from the Penrose transform. And this seems to be related to the fact that it's actually the bilocal boundary operator, which is just the parent of the local operators that give the higher spin multiplet itself.
Thank you.
Okay, more questions?
Can I make a comment on this?
Yes, please.
Yeah. So there are several comments, different types. Well, first, indeed, this particular solution is extremely special. It's associated with some Fock vacuum, and some of the properties of this absence of attractive force is just due to this property. And actually, that is important. This is what fixes a pattern of fields and relative coupling constants uniquely. Well, this is comment number one. Just completing, maybe adding to what Yasha said. Well, comment number two is that comment number two is that black holes admit a formulation in a usual GR such that the linearized solution is the same time solves the full nonlinear equations. So from that perspective, working with a linearized solution is actually a very important part of the story. That's number two. And number three is that, this is what related to the issue of locality and non-locality in higher spin theories. The way how we found with Slava the solution was, indeed, it formally solved the field equations and exhibit some proper behavior at infinity. But what was not clear whether we use the proper choice of field variables and gauge conditions. And this is still an open question that if we want to go beyond the linearized approximation, we should probably now follow. And this is partly was already done, and Slava can maybe say more about this. To use the present form and present formulation of higher spin equations where locality is under control up to really high level, let's say. So I don't know if this answers Mitya's questions, or maybe he meant something else. But
I asked about this.
Yeah, okay. Thank you.
So we have 3 minutes to stop discussions. If there are some questions, comments.
Well, Joseph, I think if we go for 5 more minutes, if there are interesting questions, why don't discuss?
Okay.
There is
yes, Maxim, please.
Okay, hello. Thanks. I have a question to Alexei regarding this weak Lagrangians. So, in case of the standard for dimensional high spin theory, you have a sort of weak Lagrangian of this presymplectic type, and if you take a linearized, if you take quadratic approximation to this Lagrangian, in which sense it is equivalent to Fronsdal? I assume locally it is not equivalent, but still the same degrees of freedom. What is precisely the state?
In the same sense that you mentioned that it describes the same degrees of freedom. We have a full spectrum of higher spin fields with proper equations of motion, but certainly this is not the Fronsdal Lagrangian. It is another alternative description of free higher spin fields. Let me make some point concerning integrating multiplier for the inverse problem of calculus of variation. It seems that there is some misunderstanding of this concept. It is not a Lagrange multiplier. What we do, we do not multiply equations of motion by some new field. This omega, this presymplectic structure, is a field which built out of the original fields, omega and c. So our Lagrangian, for example, doesn't vanish on shell. So it is rather non-trivial thing. It is not that silly, just multiply equations by some new field and you are done. Okay.
If you have a situation with the same degrees of freedom like in the Fronsdal case, you can expect there is some kind of field redefinition to reduce your formulation to Fronsdal's one.
But it is non-local. That's the point.
It may be non-local. It's like Penrose transform, if you wish.
But a local transformation can change the order of derivatives.
Yeah.
We speak
Okay.
about solution space, not about
Okay.
form of equations of motion. The solution space describe a reducible representation of anti-de Sitter group or Poincare group, or some direct sum of representations. So,
Okay. Please, some more questions, comments. So I don't see the hands. Nicholas, please.
Yeah, just a reaction to Alexei's reaction. Well, our action is not simply Lagrange multiplier times field equations. We have more P structure. So it's not.
That was my point.
You use the word silly. Of course, many things can be considered as silly afterwards, but okay.
Yeah.
Well, is it, by the way, related to the
Nicholas, Dmitry?
Okay, let's finish Mikhail Andreevich, the question.
Yeah, I started without raising the hand. Somehow I lost this label for raising a hand today. I mean, it was yesterday around. Okay, anyway, so if you let me continue. So I just want to ask, I mean, there was an old proposal by Persson Dell, by Ergen Sersgen, and also I think Carlo was involved in these actions. So is this actions that you are, Alexei, discussing in your paper, is it of the same type or is it different?
Actually, I know only two proposals for action functional. One, Nicolas with Persson Dell, and the other by Lis Moulin, I suppose. And they discuss this idea to multiply equations of motion by Lagrange multiplier, but that's a separate idea. Okay, as to the Nicolas and Pierre paper, they consider AKZ sigma model, but in 5 dimensions. So they series topological, so physical degrees of freedom, they are concentrated somehow at the boundary. But our action is formulated in 4 dimensions.
Okay. I apologize for Nicola, by the way, I forgot indeed he was involved in this work. Okay, thank you.
Dima, your question?
Also to Alexei, can you, I don't know, somehow like make connections concerning your charges that you constructed in usual theories like Maxwell or Young-Mills? So these charges, surface charges and other charges that you constructed, how would they look like?
For example, in Maxwell theory, we just take, for example, the strength tensor for Maxwell field F, and then dualize it. So it gives us some two form which on shell closed. And integrating these two form over two surfaces, we get the net charge enclosed by these two sphere, right? This is how it looks in Maxwell theory. But in, for example, Young-Mills theory, there is no such thing as surface charge because of non-linearity. That was the point. But in high-spin gravity, highly non-linear, highly non-local, we have some surface charge.
But are you sure that these are the same? Like, if you rephrase Maxwell in this form, right? So you use some special form of like equations of motion. So if you do the same procedure with Maxwell equations, and then you classify, well, conserve like two forms or whatever you need for this, you will get exactly what you just described.
As a part of our charges, you can refer these are surface charges of surface charge for Maxwell equations, of course, sure.
So I understand that those things that you describe are also surface charges, but maybe the charges that you describe are different ones. Maybe like if you evaluate them, they will turn out to be like infinite or something.
No. In the Maxwell sector, they're the same. There is no other charges for Maxwell field than the dual of strength tensor. What is surprising that you are able to construct surface charges for all higher spins in non-linear theory. This is a big surprise.
Let me interfere to this discussion a little bit. Even when you are talking about Maxwell, you assume that there is no current on the right-hand side, right?
Yes.
And this
Yeah,
is
I mean, yeah, you might
yeah.
keep saying.
Let me
Yeah,
just
yeah.
finish.
Mhm.
Yeah. So the point is that this is precisely the reason why the charges at boundary of space-time at boundary appear and surface charges appear, because the currents, they go to zero. So the point is that in the machinery of high-spin theory and allowing some non-local stories, you can even find charges in the presence of conserved charges in presence of non-linearities like charges on the right-hand side. So this is what makes difference. This is where non-locality becomes 100% important. I think there is no big difference between higher spins and lower spins from that perspective. In higher spin theory, it's just natural. There is a natural way to describe these charges. Okay, thank you.
Sorry, it seems we have to stop because if we don't stop, there should be a delay in the next section. Okay? Okay, so in this case, thanks to all speakers, so thanks to all participants. The session is over. So next session will be at 13:30.
Let me make just a little announcement. So this session is over, but I want to use this Zoom session to talk to some people that I agreed. So I've asked not to switch off the translation. So I had some preliminary agreement to talk to people. It's not a general discussion session anymore.
Okay.